In mathematical logic, we always start by some definitions, then we introduce some examples, then lemma and theorems. The very first definition is the statement or mathematical statement or proposition. A statement or a proposition is a sentence that is true or false, but it's not both at the same time. For example, let me give you two simple algebraic examples. The very first one says, well, 2 plus 2 equals to 4. Obviously, this is a true statement. The second statement says 2 plus 2 equals to 5. It is a false statement. Both of these statements are mathematical statements because we can check their truth and falsity. We usually denote mathematical statements with letters like P, Q, R, and so on. So note that both P, which says 2 plus 2 is 4, and statement Q that says 2 plus 2 is 5 are mathematical statements. Again, it doesn't matter if they are true or false. As long as we can identify if they are true or false, then those are mathematical statements. So statement P can be true. We can check if it's false as well. Another statement like Q, we can check to see if it's true or if it's false. Another statement can be R. Again, we can check to see if it's true or false. Remember that statements like I like Apple products is not a mathematical statement. We always need to be able to recognize if they are true or false. In order to make it simpler for us to track these down, we're going to define something that we call a truth table. Truth tables also help us to basically take a look at the combination or more complex statements. If P is a statement, we can define its negation. The negation of P or not P is denoted as tilde P. If statement P is true, its negation is false. If statement P is true, the negation is false, and if it's false, the negation is true. So for example, take a look at the statements up here. Statement P, for example, saying that, hey, 2 plus 2 is 4. We know that this is a true statement. The negation of P saying that, not that 2 plus 2 is 4. So obviously, this is a false statement. So if P is true, its opposite is false. If P is false, its opposite is true. We can form something that we call a truth table to track these down. In the truth table, you're going to list the statement on the left-hand side and the new statement on the right-hand side. So if P is a true statement, its opposite is false. And if P is a false statement, its opposite is true. This is called a truth table. So as we saw before, for example, if P statement is saying that 2 plus 2 is 4, which is a true statement, its opposite is false. Let's make it more interesting. Now suppose we want to combine two statements together and construct something that we call a compound statement. We're going to use the connector disjunction. If P and Q are statement variables, the conjunction of P and Q is P and Q. So the connector conjunction and denoted by P and Q. It's true when and only when both P and Q are true. If P or Q, one of them, is false or both of them are false, the conjunction is false as well. So let's see how we can build the truth table for it. The very first statement, P. The second statement, Q. And their conjunction, which is P and Q. Take a look at this. How many combinations do we have? So if P is true, Q is true, P and Q is a true statement. This is the very first combination. If P is true, Q is false, based on the definition of conjunction, P and Q must be false. Let's take a look at another combination. If P is false and Q is true, based on the definition of conjunction, false and true must be false. And finally, the last combination, if P is false, Q is false, P and Q false and false must be false. So as you can see here, you have 4 combinations. True, true is true, true, false is false, false, true is false, false, false is false. That's how we define conjunction between 2 mathematical statements. So think of these connectors as the way that we are combining statements or sentences and define something new. So again, we use these connectors we use conjunction that we denote by and to connect 2 or more statements. Let's take a look at another example. Another connector that basically connects 2 statements together. So far we talked about conjunction. Now we're going to talk about disjunction. Suppose we have 2 statements like P and Q. The disjunction between these 2 statements is P or Q, that is denoted by P or Q. It is true when either P is true or Q is true or both of them are true. It's going to be false only when both P and Q are false. We can take a look at their truth table as well. For the truth table, so based on the definition, we have P, we have Q, and P or Q, their disjunction. As before, we need to take a look at all possible combinations. P is true, Q is true as well. True or true is always true. This is following the definition of disjunction, everyone. If P is true, Q be false. False or true, true or false is always true. P might be a false statement. Q might be true. False or true, based on the definition of disjunction, is true. Both of them might be false at the same time. False or false is always false. So again, take a look at the definition. True or true is true. True or false is true. False or true is true. False or false is false, everyone. So this is the truth table for disjunction. Again, we are using these connectors to define a new statement, a complex or compound statement. We use these connectors to define a compound or more complex statements. I want you to pay attention here. For both of these cases, we have two statements and we end up with four combinations. First combination, second combination, the third combination, the fourth combination. The same here. Two statements, one combination, two combinations, three combinations, and four combinations. So the question is, if I have, for example, three statements, how many combinations I get? So in general, you're going to have 2 to power n combinations or rows. So if you have two statements, 2 to power 2 is 4 combinations. If you have three statements, PQR, if you have just P and Q, you get 4 combinations. If you have P, Q, and R, you get 2 to power 3 or 8 combinations. If you have 4 statements like P, Q, R, and S, then you have 2 to power 4 or 16 combinations. We're going to go over some of the examples so you feel more comfortable about these combinations later. Very well. The last one that I wanted to talk about is exclusive OR. Let's take a look at next definition. A statement form or propositional form is an expression made up of a statement variables like P, Q, and R, and logical connectives or logical connectors such as negation, and, or that becomes a statement when actual statements are substituted for these mathematical components. We also talked about the truth table. For a given statement, it basically displays or tracked the true values for those compound statements. And again, as I mentioned before, if you have two statements like P and Q, you get 4 combinations. If you have 3 statements, you get 8 combinations. If you have 4 statements, you get 16 combinations. And in general, if you have P1, P2, P3, and propositional statements, you get 2 to power n combinations or rows for your truth table. Let's take a look at another important definition. Here we're going to define something that we call exclusive OR. Exclusive OR, which is denoted by a circle and a plus sign inside of it, is basically a connector that is useful in engineering. For example, if you have two statements like P and Q, if you try to connect them with exclusive OR, the definition saying that, hey, you have P or Q and the negation of P and Q. So based on the definition, you're going to form a truth table, correct? So here I have my P, I have my Q, P exclusive or Q. So if P is true, Q is true, you get true or true, and the negation of true and true. This is just true, this is just true. The negation of true is false, false and true is false. Let's take a look at the second combination. If P is true and Q is false, then you have true or false, and the negation of true and false, true and false. So take a look at this. True or false is true. True and false is false. The negation of false is true. True and true is true. You can check the rest of them as well. If the first statement is false and the second statement is true, you're going to end up with true as well. If both of these statements are false, you're going to end up with false. So basically, what does it tell us? It tells us as long as the two statements have the exact same truth value, the combination is false. So true, true gives you false, false, false gives you false. But if they have different truth values, it's going to be a true statement. So again, exclusive OR is important, especially in engineering. Now we're going to go over examples, everyone.